Hi, I'm Daniel Jeffries, the Managing Director of the AI Infrastructure Alliance, and today we're going to talk about the entire AI ecosystem and what it looks like for 2022. That's going to give you a chance to figure out what you should be spending your precious time, resources, money on when you're looking at bringing components into your infrastructure, expanding your team, expanding your ML work, and putting it all together into the bigger picture. The challenge in this space is massive. There's the AI ML landscape. It's vast, it's complex, it's rapidly evolving. There is a Cambrian explosion of new ML software and services, and it's really hard to figure out which pieces you need and why and when, especially at different sizes of your team. You know, the kinds of tools that you need when you have one ML engineer with a laptop and putting maybe first model into production is vastly different from when you're putting 10 or 20 models into production. You've got 20 or 30 people on the team, and that's vastly different from when you're training on a supercomputing cluster and putting thousands of models into production, and you've got all kinds of data engineers and support teams in there. The challenge, of course, is that there's just no clear, reliable guides. The guides that are out there are all kind of slanted in this particular direction, usually to sell somebody this particular piece of software. And the IA is here really to help people understand it in a neutral fashion. We've got 40 plus different companies, 5 or 6 different communities in here. And so we come at it from a very broad perspective and try to give you kind of the most neutral information possible in the most fair way possible so that you can make the correct decisions. And that's going to bring clarity to this very complex to understand space. The big deal that we put out this year is the AI Infrastructure Ecosystem Report of 2022. You can get it right from the website. It's free. And it's going to give your team leads, your technical executives, your architects, the keys they need to build and expand their infrastructure. It's providing a comprehensive, clear overview of the entire AI/ML landscape. So you're going to know what kind of folks I need at the time, what kind of tools I need. If you've already got tools in there, you're going to be able to figure out where the other ones kind of fit in there. So we did a giant survey in the report, 300 different companies, anywhere from 10 million in revenue to over $1 billion in revenue. And what we consistently found is that people are generally not satisfied with the current state of their infrastructure. Only 26% of folks are very satisfied with their infrastructure. 55% are somewhat satisfied, and it just kind of goes downhill from there. So the good news is there's room for improvement, right? A lot of room for improvement. And the nice thing is there's so many different kind of tools out there. Hundreds are covered in the report, but there's probably 500 or 600 on the marketplace. And so there's a lot of choice within the field. It's a great time to be in AI/ML because you really have your pick. Now, choosing the right architecture is a classic problem that we see kind of across everything from IT and business, et cetera. This wasn't new to AI/ML, right? And this is the build versus buy versus best of breed. We're going to talk about the IA's perspective. We take a very definitive stance on this. Now, build your own has been how most companies have done it. All engineering companies, if you're looking at Google, DeepMind, OpenAI, Tesla, Netflix, all these kind of gigantic tech companies, they started taking AI and ML out of the research labs, right, and bringing it into the real world, building products, classifiers, enhancing their own business. So they had little choice but to build their own solutions from scratch for training, deploying, and running the models. The IA does not recommend that most companies take this approach, and that is, it requires a huge amount of technical debt, a tremendous amount of technical teams to maintain it. It can be obsolete quickly. Sometimes you can go down a pathway where you build something and it doesn't turn out to be, generally usable across multiple types of AI/ML problems. And so really, this is really for only some of the largest teams. That doesn't mean you might not build some of your components, that you might not build some glue code to unite them together, maybe an interface or layer an API over some of the different pieces that are out there. But building your own tools from scratch, there's a lot of wonderful open source projects and companies out there, and we don't recommend this except for the biggest teams. Buying end to end. Now, this is the second kind of, there's a siren song of like, give me the unified system that does absolutely everything. I want it to be able to do, train gigantic distributed, neural nets and small analytics engines. I want it to be able to process text and unstructured data, video, images. I want it to be able to do monitoring and management, inference, deployment, data engineering, all this stuff. And the fact is, we're just not there yet in terms of the evolution of the industry. Every industry goes through a diffusion of innovation curve where there's early adopters, early pioneers to kind of early majority to late majority to those kinds of things. And the fact is, the ecosystem is very characteristic of an early stage ecosystem. In other words, early and leaning into early majority. So if you look at kind of the car industry, there were probably 300 or 400 different car companies in the early days. One specializing in making windshield wipers or windows. Over time, a lot of these companies consolidate. The talents consolidates. Maybe you end up with 10 or 15 major car companies in the world and a dozen or 20 different suppliers of various components and parts to all of them. And so that happens over time, but we're nowhere near kind of the Wintel Dynasty stage or the just buy VMware if you want to do virtualization because they figured it out. Just pick this cloud to do it. We're not there yet with AML. And so there's just too many different things in the space that are happening at the same time, too many different aspects of it, from monitoring and management to training to deployment to data engineering, et cetera. All of these things, it's very challenging for any one company to be good at it. It doesn't mean they're not going to get there yet, but in this time, you're not going to be able to find the one tool to rule them all, despite some marketing that might say that you will. So we advocate very much for the best breed, and that is for anyone from small to advanced, to medium to advanced data science teams and data engineering teams. You're going to take a modular approach to building out your AML stack. We recommend that you build there's 1 to 2 core platforms. Get all the information, see all the pieces that are out there, understand what their capabilities are, get that information, look at the different things across data processing, pipelining, versioning, lineage, experiment tracking, deployment. And after you've selected 1 or 2 core platforms, then you can more easily choose satellite platforms that fit your specific needs. You might run a little glue code, as we talked about earlier. The best of breed is going to be the best challenge, the best thing for the vast majority of companies that are out there today, unless they, for instance, have a very simple use case or one kind of use cases over and over again. There might be a single platform that can kind of handle, I'm just doing this basic analytics things over and over. But the truth is you're probably having multiple pieces in your stack, and you're going to have that for many years. How long did it take for you to get the benefits from AI/ML to outweigh the cost of the infrastructure, the implementation, the personnel, right? The people setting it up and the infrastructure. And the vast majority of folks were able to realize within 2+ years a return on their investment. And that's wonderful. A lot of times, if you look at kind of the history of enterprise tech, sometimes these things have taken a lot longer, or there's always kind of a cost thing. And the beautiful thing about artificial intelligence is that it can drive real value across the business, across the vertical, and that's really exciting. Of course, there are still some, where the costs still outweigh the benefit. Some are able to do it even faster. Like I said, 1 to 2 years. Some take 2+ years. But the vast majority of folks do get a tremendous amount of benefit in a relatively short period of time if they choose wisely, and they're not swapping out that infrastructure because they chose it based on one use case that didn't expand out to other use cases. That's very important. Thinking about not just the use cases that you have right now, but the use cases that you might have in the near term, 6 months, a year, several years from now, or in the future, that you're building a platform that's flexible enough to deal with not just the one problem you're trying to solve right now. So let's make sense of it all. There's the godfather of neural nets, generated by an AI in the style of Norman Rockwell, Jeffries. You can forget the NASCAR slide. The NASCAR slide is one where you've got a box, with the 86 categories of machine learning, and each logo neatly fits into each of these categories that we just completely made up. This was, a cutting edge kind of slide back when Bloomberg did this 6 or 7 years ago. But now every marketer has kind of taken this thing. They make up a completely, wild set of categories that make no sense, and they take AWS and Databricks and Pachyderm and Y Labs and Rise or whatever else, and plot them into one tiny little spot. This makes no sense. It makes sense to marketers, at first glance, you look at it and think, oh, yeah, of course, I'm getting a lot of good information, but you're not. The truth is, products don't just fall into one random category. Okay, so at the AI Alliance, we came up with blueprints. We've got a new revision of the blueprints coming out now, but this is the one the reports are based on. And this is a classical stack, right? Where we've kind of broken it down based on your standard infrastructure. These are your core pieces in the middle of your data engineering, experimentation, training, deployment, and serving. We call it a pipeline, but it is very kind of a loopy kind of thing where you're going back and forth. We broke it between data engineering, which tends to be focused on gathering the data, cleaning it, fixing it, and data science, which tends to be experimentation, to deployment, to serving and inference, these kinds of things. There's external data sources, synthetic data, logging engines, monitoring. And you can see that they kind of cut across these 5 core spots of data engineering to serving. And it's not that one company's logo fits right here and another one fits right here. The answer is that each platform actually does multiple things and it changes over time. Their products are not static. The projects are not static. They're adding new features all the time. So if you look at something like Ray, for instance, right, it started off as a reinforcement learning project and then a serving engine, but now it's doing training and a whole bunch of other things. So it expands over time. And so the idea was that we could show no support, full support with a dark color and partial color to show partial support of the different thing. And this kind of lets you get a clear idea in your mind of where these different open source tools and platforms are able to provide value in your stack. And then in addition to that, you're able to take different companies, different projects, layer them together into a complete stack and see that all of your kind of aspects are covered. So, company E might cover deployment and your model repo to serving, whereas company A might cover your data science experimentation and training, experimentation engine. There might be overlap in terms of the metadata store or the notebooks where 2 companies are kind of covering that for you. And so, this is how you're able to kind of get a picture of how all the best of breed fits together. So let's talk about kind of the key categories. So one thing that I've always been, again, disappointed about with the NASCAR slide is they didn't really distill the categories down far enough. In other words, truth is that which cannot be simpler. If I'm struggling to figure out where things fit, it means I haven't kind of distilled it down far enough. And so we did our best to kind of distill it down into very broad categories that kind of allowed different tools cleanly to fit in there. And the kind of the first thing that you're going to be looking at most likely, and this is likely to be your core engine across the board, depending on the things that you're doing, are going to be your orchestration pipelines and compute engines. And orchestrators are the control engines of AI/ML. They organize everything from how the data is ingested and cleaned, how it's transformed, how it's trained and tuned, to the deployment of the finished model. In short, these are the puppet masters of your AI/ML workflow, and they're really one of the core contenders for your core platform choice. So if you look at the data here, you're going to look at, this is from our survey as well, you're going to see which components in the infrastructure are going to have the biggest results. And this is kind of surprising. A couple of years ago, we looked at things like deploying to production was number one, and there was that stat that said, oh, great, 87% of models never get there, which I think was just probably made up, but or inexacting. The truth is, a lot of people are getting their models into production, and we're going to see a stat on that later. But the vast majority of time is people are collecting that necessary data. Okay, and then cleaning it, transforming it, QAing, process it. Those are the first 2 things. And so we're seeing a lot of folks dealing with kind of the biggest thing is building those data sets, not necessarily training and deploying the models. And that was an unexpected result. And it was even more backed up by the fact that it seems that companies are hiring data engineers in a ratio of about 2 to 1 to data scientists. And I know I was just having a conversation with an MLOps engineer about this, and everyone wants to be a machine learning researcher. That's the glorious part. It's awesome. I know some amazing and brilliant ML researchers, and it's super cool. But the fact is, it's the data engineers, the MLOps engineers who spend all this time pulling data sets from 15 different sources and eliminating redundancies and cleaning it and fixing broken feeds, getting it all into a format so that it can be passed up to a higher level for the data scientist. When you look at kind of data science in the academic world and in kind of traditional use cases, it's like, here's a data set, it's already perfect, do something with it. Go download Boston housing prices once, and do something interesting with it. And the truth is, there are 5 or 6 different steps before that of like where the data came from and how it was cleaned and where there are broken fields and redundant fields and these kinds of things that had to be done in order to get that into a clean state. The data is not fixed, changing over time. And we're seeing that with a lot of the kind of data-centric AI movement and those things that are coming to pass, where people are focusing less on tweaking the models and essentially more on tweaking the data set and getting that correct. So data engineering, incredibly important, and the tools that support that, incredibly important. So that's where I want to draw your attention. We talked about orchestration being the puppet master. We've broken that into data engineering. We've broken it into model orchestration. But in this case, there's an even higher order of abstraction that you want to think about when you're thinking about your orchestration engines. From the eye's perspective, there are 2 major types of orchestration. There's what we call loosely coupled and tightly coupled, and these are our terms that we discovered after studying hundreds of tools on the market. Each of them have their advantages and disadvantages. The basic difference between them is simple. A loosely coupled orchestration engine is not tied to the underlying execution layer. So Airflow is an example of a loosely coupled orchestrator. So is something like Argo. It doesn't have a dedicated compute and scheduling engine that's tightly tied to that. It's a way to say execute these steps in this particular way. A tightly coupled orchestration system are tightly bound to their underlying compute engine. Spark or Pachyderm or something like that is a perfect example because it's its own orchestrator layer, but it also has the compute big data processing engine underneath it, and it's very tightly coupled to it. What does it look like on the current trends in the next years? These 2 things, when you look at them, by the way, if we go back one slide, actually, I'm going to do that. Let me do that. If we think about loosely coupled and tightly coupled, loosely coupled is actually going to be able to give you it's going to make it so that you're able to orchestrate across a lot of different platforms. So if you end up having Spark and Ray and a bunch of other things in there, that's going to give you a chance to be able to orchestrate across a lot of those platforms. The downside of loosely coupled is it doesn't have as deep an understanding of the underlying compute engine, right? And so that's where if you have a heterogeneous environment, a lot of different pieces under there, loosely coupled is going to be really interesting to you. However, if you have a tightly coupled engine, it's going to have a deep understanding of how things are scheduled, where they're scheduled, data parallelization, tensor parallelization, these kinds of things underneath the scene, and it's going to be able to call those very easily within the orchestration layer and the API. That's how you want to look at these 2 things. In practice, you may end up having both kinds of things, within the space. But in the short term, you're going to have to decide how many kinds of tools you have in there and which one kind of fits your way. So that's good. I wanted to go back there and kind of make sure you got that point because it was a clear one. So what are the current trends over the next 5 years? Orchestration and compute are essentially one of the most essential components in AML. They're the bedrock of how the work gets done on the system. And making a bad choice in this framework can prove very, very costly. Orchestrators, pipelines connect with almost all our aspects of the system. And so making a bad choice here can really come back to haunt you. So companies looking to make a decision on which platform they should choose, they want to look at the key capabilities of their team. Are they strong programmers? Or do they need a powerful visual GUI or both? You want to look at the range of capabilities of the platform, the kinds of AML projects that you need to support. Is it structured, semi-structured, unstructured, all of the above? Most of the platforms play well in one or the other. Some of them claim to be able to do both effectively. They each have their trade-offs, so that's really important to kind of look at. If you're going to be doing a lot of video and audio and imagery versus doing a lot of database work, those tend to be kind of different sort of tools. The customer team and support, you're going to need that. How much support do you have? Proprietary tooling capabilities. What is the graphical front end? So there's a lot of different things that you want to look at in terms of how you put these things together. And where it goes over the next 5 years. We expect to see some consolidation in this space as people kind of standardize and sort of standard ways to do things. And we expect 1 or 2 sort of orchestration engines, maybe 5 or 6, to really push ahead of the curve in the next 3 to 5 years. And so you want to choose wisely in this case. So now let's take a look at something like model serving and deployment. Everybody's serving and deployment. Let's take a look at this. Over the last few decades, traditional code-based application deployment have evolved, right? So we went from these very monolithic type of deployments to these faster, more agile and DevOps style automated rollouts with automated testing. And AI/ML builds on deployments, build on a lot of those foundations. But AI models represent some very different factors and challenges that make them more challenging to deploy at scale. In a 2020 report, Algorithmia, which is now a data robot, said that only 14% of organizations were able to deploy a model in 0 to 7 days. And they reported that 28% took 8 to 30 days, and most people are taking a lot longer. Our numbers 2 years later show something different. It shows that the numbers have in fact changed. Teams are getting better and faster at getting those models into production. Many are still struggling though, right? It's 34% can get them in there 30 days or less. Some of them get it in there a week or a day. Some are still taking 2 to 3 months, 6 months, or a year. So there is room for improvement, but it's time to put to bed that statistic that most of the models aren't making it into production, or teams need the most help. There's some very effective deployment serving frameworks out there that have helped automate more and more of this process. That said, though, it still can be the hardest thing to plan for. If you'll notice, the time it takes to productionize a model is one of the hardest things to operationalize an AI/ML infrastructure. And that is, even if a company is getting 50 or 100 models into production, it might be 2 or 3 or 4 of those models that were very challenging to plan for, with all kinds of dependencies and the strange things that they needed access to and open ports, et cetera, that make it incredibly challenging, right? And so planning to productionize models and deployment is still a challenge. So picking a good deployment engine is key. Now, what is really the difference? From the ICE perspective, again, there's 2 different things. Deployment is a workflow. It's human-based with software. That's the workflow to get a trained model into production, the steps that you're going to take to get there, automated or manual or both. Serving is the platform that hosts and serves the model response to requests, similar to Nginx or Apache or things like that in the web world. This is where the inference requests are being served. And so when we're talking about these platforms, we tend to be talking about platforms that kind of serve both a deployment engine and a serving engine, but they need not be the same thing. There are engines that deal just with the workflow. And so, in fact, some of the orchestrators can deal with some of these things as well. And then there's kind of large-scale serving platforms that can deal with serving at a huge scale. Let's get on to the next thing that we're calling. So this is monitoring, observability, explainability. Now, these tools are often used interchangeably in the industry. And in fact, they're not interchangeable. They all have very sort of specific meanings when it comes to artificial intelligence and machine learning. So we coined a new term, AI supervision. It's starting to get into a larger lexicon of folks who are using it. Supervision has some other meanings in ML, meaning like supervised learning, semi-supervised learning. That's not what we're talking. We're talking about kind of something that's able to oversee all of the different aspects of what's happening in your data, your models, et cetera. And each one of these things is separate in terms of what they do. So typically, how we define it is this. Monitoring is trying to answer the questions of what and when. This is similar to traditional monitoring that we have right now in the web sphere, right? Is the web server up or down? When did it go down? When did it come back up? These are monitoring capabilities that track most closely with traditional IT monitoring, including uptime, performance, and the like. But there's also, inference speed, those kinds of things. But those are similar to how fast is the website responding. Observability is different. It gives teams context into the how and why. The model went down because the last deployment created instabilities that caused it to crash after 10 minutes. It helps answer questions like, why is the model's prediction performance degrading? So this is sort of a deep view into the monitor, right? And it's also how you suss out particular types of problems, for instance, before you even get to production sometimes, right? So if I've trained up a fraud prediction model and I look at the features and it's focused on the person's age, that may be an effective model, or it may be overly focused on age. And we may have some younger folks who are, able to, afford a loan, and some older folks who can't. And the model, because it's overly focused on that one feature, is missing a whole bunch of potential customers. And so that kind of observability gives you an understanding into whether the model is doing what you want it to do, or how it's making decisions. And that's kind of critical as you're working through the pipeline. Explainability is basically a suite of algorithms that tend to help after the fact, right? We want to understand why the model made a decision after it's made that decision. Maybe it made self-driving car veered off the road, or a classifier labeled a children's toy as a horse instead of a children's toy. And so we want to understand, what was it thinking, quote unquote. And a lot of the explainability algorithms are about how and why the model. It's kind of peeling back the black box to get a better understanding. Again, you don't want to think of AI monitoring observability as really the same thing as traditional IT monitoring due to its unique characteristics, right? And again, that's why we coined that term AI supervision, and to include all the different aspects of monitoring observability. Even if you're going to a particular platform and they're using these terms more loosely, they've labeled everything under observability or monitoring, et cetera. Don't be taken in by that. Use the kind of precise definition so that you understand the range of capabilities and you can interrogate that platform to understand what they're good at. Are they really just kind of Prometheus and Grafana and monitoring, speed and deployment and those kinds of things? Or are they able to actually dig into like the kinds of features that are being chosen, the features of the data set? Are they able to explain what happens when a model happens, when a model makes a decision or even a good decision? And we want to be able to touch on all these different things in our choices. Now let's get to training. Training is one of the major bottlenecks in machine learning alongside labeling. And it's one of the things where the human is kind of out of the loop for a period of time and you're waiting for the machine to do those things. Whereas labeling is slow because it requires scaling a distributed human labor team. Training is slow because it involves waiting for machines to finish complex calculations. It's also the most systems administration heavy aspect of an AML pipeline. Again, it's amazing when a brand new model comes out and does all these wonderful things, but it's really the data engineers, MLOps engineers that are supporting these gigantic clusters and the ability to train these things over time using specialized processors like GPUs or TPUs, managing Kubernetes, spinning up pods, allowing these things to happen. So if in our survey, training ranked third on the list of biggest challenges companies face when building their infrastructure. Now, what's interesting is that if you're doing white analytics or a lot of these kind of basic classifier systems and things like that, then you're probably not going to run into massive amounts of training hurdles, right? You can get yourself some big GPUs in the cloud, maybe a small cluster of them, and you're going to be able to kind of rapidly train a lot of these different models. Once you start getting into larger deep neural nets, these kind of large language models, or you get into big transformers, things of that nature, large classifiers with a lot of data that's happening over time, that's where training starts to become a serious bottleneck. It's very challenging to scale linearly across a lot of these GPUs. And what you start to see is there are companies that kind of specialize in some of these different things that are out there. So you see things like Determined AI, Horovod, Colossal AI, Deep Dream, which came out of Microsoft, and the Megatron model. These kinds of things that are able to kind of parallelize across lots of DPUs. But right after collecting the necessary data and cleaning it and everything is training those models. So really the first part of that infrastructure, pulling all the data in, working on it, et cetera, training it is where people are going to spend 60 to 70% of their time versus the deployment, inference, and monitoring of the models. Over the next 5 years, and it's important for us to kind of look at this, many organizations are not yet training large numbers of models or training models consistently enough to justify advanced training capabilities. However, we're starting to see a shift now. In the early days, folks were focused on basic analytics and kind of getting their feet wet. More and more companies are starting to leverage, machine learning, and this means more like transformers and fine tuning models that are out there, like GPT, 3 or any of the variants of it, Chinchilla, et cetera. And to do that, that's where they start to get into needing, lots of GPUs and tensor ASICs and those kinds of things. The various public clouds offer a wide variety of hardware and skilled IT teams, and teams that can build their own Kubernetes instances and Slurm instances, and leverage the kind of open source training framework, Horovod, Colossal AI, PyTorch, Deep Speed. These things are going to be things that you're going to start to become, more and more teams are going to start to become familiar with over the next 3 to 5 years as we move from sort of baseline analytics into more and more machine learning, because machine learning is where the real advanced capabilities come from, whether that's text image generation, or whether that's spotting things in images, or advanced pathfinding, or text generation, or question answering, discovering proteins, playing games. These kinds of things are incredibly machine learning and compute intensive. And the teams with the most data, the most GPUs, the most talent are going to be able to leverage these. And that's where you're going to start to need to get used to these kind of big training frameworks. In the short term, using some of the clouds and leveraging some of the tools that they already have set and their kind of massive budgets for these types of tools is great. And then, advanced teams are able to kind of build their own supercomputing in a box, but things that come out of Lambda, or our wonderful partners NVIDIA, and their incredible DGX boxes with stuffed with A100s, some of the most coveted chips in the world, and the soon to be released H100s. Let's talk about a topic that's a bit sort of closer to my heart in terms of I spent a good chunk of time at Pachyderm, where we work on data versioning and lineage, but a number of companies are really starting to work on data versioning and lineage. This is a problem that you don't necessarily know that you have until later in the cycle. You might have already gotten good at using, Argo and Kubernetes and, maybe Ray or, something else to kind of do, inference and those kinds of things. You've got, monitoring and management engines, and you're able to look at, what's happening in your models. But really, data versioning and lineage becomes very important when you're dealing with lots of data over time, and the model, the code, and the data itself are changing over time. Now, in the past, we weren't really able to deal with this in an effective manner. We were able to do snapshots in kind of the virtualization era, but we were able to do those in an ad hoc fashion, an annual fashion, very slow. With with object stores in the clouds, we essentially have infinite storage on the back end for anyone concerned. We could take generally an infinite version of an infinite number of snapshots, so we can really keep lots of snapshots of the data and be able to go back and roll forward and backwards at any point in time. So versioning is keeping different snapshots of data. This is important to differentiate between these terms. Lineage is what is in all those snapshots. So if you go back to that earlier analogy of when I would take snapshots before I did a VMware upgrade on maybe an Exchange server, I might take the snapshot and type, Dan's snapshot, et cetera, right before I did the upgrade. But really, when I'm taking lots and lots and lots of snapshots as the data is changing, I really have no idea what's in it. So lineage, you need an automated fashion to keep track of those things. It's not enough for the administrator to manually kind of put those things anymore. So you need an automated way to look at the data lineage, where things have branched and changed over time in the DAG, and how you can kind of roll backwards or forwards in time, how the data got from the beginning to end to where it is now. And there's a lot of times in versioning and lineage in the industry. We've seen versioning and lineage in traditional software coding, CVS to version today with Git. However, versioning and lineage of data is relatively new. And there are a number of approaches to data versioning and lineage. CI divides these approaches into two types of versioning: versioning of databases and versioning of files and object stores. Of the two, the versioning of files has the longest history and the most development. The versioning of databases is a new phenomenon, and it's largely mirrored the rise of machine learning, but it is catching on quickly. Versioning there is of the databases is something that generally has not been done. In other words, if you look at Oracle or things like that, the versioning was not really a thing there. It was mostly snapshotting or backups, and that's different. There has been versioning of schemas in databases. But generally, this idea that you would actually have a complete version of all the changes within the database is a new phenomenon. And it's something, again, if you have a lot of text data, structured data, these kinds of things that you're going to want to start to look to in the near future. Versioning of files and object stores is very different, and a number of different folks take a different approach to this. Many of them take inspiration from Git. A couple of the platforms choose Git itself, but Git is not actually a great choice for this. In other words, Git is primarily good for small amounts of data or distributed coders. But if I have half a petabyte of data, I'm not downloading it over the internet and replicating it to a bunch of places. So typically the data is going to be centralized on an object store, and the system is going to take inspiration from Git using pointers or a copy on write file system that overlays that object store. And you don't want something that's doing pointers to something that you don't actually have control over, right? Because if you don't actually have ironclad kind of immutability underneath that, then the problem is that Git can then point to a state of the data that doesn't exist. A good example would be something like if I've got a million files that are 1020, images, a million images that are 1024 by 768, and I have them in a directory, and I record, 50 different model training runs off of it. Then an administrator comes along and crunches those images down to 512 by 512 and overwrites them. If I don't have ironclad immutability and snapshotting at the file system level, then what happens is I now have 50 training runs that point to a state of data that no longer exists without rolling back to a backup. You do want ironclad immutability. Again, Git is not particularly good at this centralized kind of data. So most of the teams out there take inspiration from it, but don't use it directly. The other thing that you want to look at when you think about versioning and lineage is how long is it? And many of the companies out there take a very sort of short-lived version of it. Something maybe like, for instance, Databricks does it at something like 7 days, right, before it's tombstone. And that's useful for experimentation and training, but it's not useful for sort of long-term versioning and lineage. And that's really important, depending upon your use case. And in some cases, for instance, if you, we're training an image recognition system for products in your store and facial recognition of folks coming into the store so that they could take things out of the shopping cart and just check out automatically without ever having to go through checkout itself. You might have the GDPR when someone has a right to be forgotten, for instance, and they might want to be taken out of the database. And if you only had 7 days at that point, it would be a disaster. You wouldn't be able to go back 3 months or 6 months or a year to find out where that is and kind of kick off a retraining of the model. So there's a lot of aspects to thinking about data versioning and lineage. Typically, you're talking about it from a file and object store. It's got to be integrated into your orchestrations and your pipelines. It's generally going to take inspiration from Git. And this is a new problem. Again, it's one that people don't tend to think about until it's too late. That's something you want to be thinking about from the very beginning if you're designing an advanced machine learning system. Labeling. Labeling is the next gigantic bottleneck. And that's the process of adding tags and metadata to raw data like video, images, text, audio. The annotated data codifies the kinds of knowledge and features that we want the model to learn. Data labeling is, again, historically the largest bottleneck in AML, because historically the only way to do it was through brute force, crowdsourcing, because getting the sheer number of labels is having a lot of people type in things, but it's error prone, it's challenges. There's a lot of recent advances that have helped augment manual data labeling by using machine learning itself to speed up the process with things like semi-supervised learning. Labeling ranks as the fourth biggest challenge teams face when building their AI/ML infrastructure. And the first one is latency, which is interesting because in academia, you generally care about your performance and beating these benchmarks. But if I build the greatest text prediction engine in the world and weave it into Gmail, and so that it can predict the next 5 or 6 words in my sentence, like, that's really nice to meet you, but it happens too slowly. If it happens slower, then I can think it or type it. Then it doesn't matter if it's 99.9999% accurate because it's too slow. And so latency is the number one thing in production. How fast can that model respond? Hiring the right people and talent is a big challenge. But if you look at labeling is number 4. It's a massive challenge. It's right up there with the others. And it's something where people spend a lot of time and resources on. At the most basic, your labeling software is all going to be relatively the same. It's going to have role-based access control. It's going to include the ability to have a team of local or distributed human labelers labeling various kinds of data, text, images, putting bounding boxes around things, etc. That is kind of the table stakes. Where you start to get into the advanced capabilities is something like we see here, where, for instance, if you've got 50 or 100 or 300 people labeling something, you want to have someone who's kind of in charge of that, and you want to have a review process. So you also want some AML built right into the pipeline. In other words, you want to look and see, is it consistent across labeler A, labeler B, labeler C? Yes, they're consistently putting the label around the fish. Whereas in this case, you're able to do some more manual QA where you feel someone has put a too small of a box around the fish, not covering the entire fish, inconsistent with the label. You want to be able to intercept that, have the reviewer say, no, that doesn't work. correct it and get it back into there. So you want a whole workflow that kind of checks the accuracy of these things, but you also want AI/ML built into the capabilities. And when you look at kind of the more advanced systems that are out there, most of that tends to be machine learning built right into the whole pipeline itself. In other words, the companies that have the most advanced skills are not the ones that just have kind of brute force. And we don't recommend just using Mechanical Turk, something like that. You want a lot of these companies have a human team of skilled folks who are trained in this kind of thing. And so you want to choose an advanced team. You don't want to choose just random folks out there on the internet. But the big advanced capabilities tend to be these sort of semi-supervised classifiers, whereas you tend to do 1,000 or 5,000 labels or 10,000 labels on a massive data set of millions of things, and then the system then learns from those labels to be able to label the rest of it. And so you're going to get some noise in those kinds of things, but those are where the advanced teams are, and a lot of the companies that are getting the big splashes in the headlines, they're there because they're working on a lot of these challenging automation steps to automate essentially what's one of the biggest bottlenecks. What's nice about some of those companies getting kind of big customers, it tells me that the field is moving along quite quickly. In other words, it tells me that customers are now at the point where they're looking at these massive data sets and they're able to figure out, like, what are we going to do with these things, right? And they're getting to the point where they're doing the labeling, bringing these types of things in. Let's get into a feature store. A feature store is a data storage system for features of machine learning models. And what is that? Really, you can think of it as a central place for storing raw, curated, documented features. What is a feature? Let's give a classic example. If I've got someone's birth date and the current date and time, I can calculate their age, and the age is the feature. And so what you want, and the reason you want a feature store, is that we found a large degree of confusion around teams why they'd actually need them. In fact, feature stores came out, they got a lot of popularity, they started showing up in every single diagram. But the fact is, they might not need to be in your diagram. They are good for medium and large size data science teams working together with lots of models that have similar characteristics. Okay, if you're a very small team, a feature store might not be all that useful to you. They become very useful when you start thinking about a medium to large size team. So in other words, if I've got if I've got 30 different teams at Uber, all working on calculating how fast the car is arriving, and they're all doing that independently, that's an utter waste of time. And so what you would rather have is the ability to capture that feature and then other teams to be able to consume that feature. And so when you really think about what a feature store is it is generally a fast in-memory database that pulls from other databases and does some transformations in order to calculate the freshest version of that feature that other teams can consume from. So it's not magic, but it is a very important characteristic for teams as they start to grow, so that they're not doing redundant work of calculating the various features that they need, and they're able to share those across their various models. Again, there tends to be two databases, a feature catalog. There's ability of transformations that are done there, generally on an external engine or in the feature store itself. And then there's kind of the serving and supervision of that, right? So, how long is it? If it is replicated, is it online? Is it offline? It's essentially a data warehouse on the back end as your first database, going to include a large amounts of offline features. And the second database is a database that offers online features at low latency. You can quickly kind of grab them for the things that you're doing. And then there's essentially two kinds of that, batch and streaming, each depending on the kinds of workloads that you can support, the kinds of company you have, the kinds of data you're working with, kinds of challenges are you trying to deal with. Are you dealing with a real-time kind of engine like Uber and getting cars there, or can you work with something in a batch transformation? For instance, like in Airbnb data, where you might not necessarily need all of the latest kind of housing prices and things like that up to the minute, but you might need it over the last couple of hours or the last couple of days. Where do we see over the current trends in the next few years? We're seeing a number of commercial feature stores come to market, and they're facing growing pressure from open source solutions. They're also facing competition from orchestrators with their own proprietary built-in feature stores. So you see ClearML, Iguazio, Databricks, Amazon SageMaker, Google Vertex, they all have their own feature stores built in. Commercial feature stores, independent feature stores are great for large teams that are going to need kind of a guaranteed response time, dedicated support. SaaS offerings help manage the complexity. However, they may not support all the desired backends that an organization needs. That's where an open source solution might come in, certainly for smaller teams or teams that need a lot of extensibility or teams that have excellent IT skills, and maybe they need to support a wide variety of backends that aren't necessarily supported out of the box, and you maybe need to extend the platform into your own backend. And we expect to see, again, consolidation in this space as people kind of standardize on a few different ways to kind of do this. There's kind of only a few different ways to kind of bake this cake. And so we expect there to be, kind of consolidation, and we expect some of the proprietary solutions or solutions that have built their own to phase those out and kind of roll in whoever the winners are in the next, 2 to 5 years. Synthetic data is one of the newest parts of machine learning, and it's essentially artificial data that isn't gathered from the real world. Now, we talked about the gathering of data and how challenging it is. Gathering that data from the real world, we're seeing that they're hiring data engineers that are rated 2 to 1, and many of the challenges are importing that data, labeling it, getting it done. So synthetic data can offer a solution to that problem. It's one of the most cutting edge domains in the entire ecosystem. It means that we can generate data programmatically. And most of the companies that are doing this are no older than 5 years. Many of them spun up in the last 2 years. Many companies we've surveyed expect synthetic data to make a big impact on their model building in the next 5 years, trailing only multimodal models and models that may be able to do models that may be able to do multiple things well. So you may not be able to get a complete data set of XYZ, but if you're able to programmatically generate parts of that data set, that can certainly make training gigantic models much, much easier. Synthetic data ranks as, again, the second biggest impact that people expect to see in the next 5 years. So this space is going to rapidly develop. It's one of the most machine learning heavy aspects of the pipeline. In fact, it really is machine learning itself that generates the synthetic data. Now, we've seen kind of a number of different things that happen in this space. So just as labeling uses machine learning to speed it up, synthetic data uses machine learning to bypass the gathering of data. Again, another challenging collection scheme. There's a few different categories here, though. There's fully synthetic. This means that the data doesn't include any data gathered from the real world. It means it was totally generated procedurally. Some of the systems that are out there are very far advanced along in this, particularly in the image model space. Because we have so many 3D engines and things like that for video games and movies, those have been leveraged in machine learning. So, for instance, if I wanted to generate, if I needed a giant database of boat crashing, I probably wouldn't be able to get enough images or video from the real world for that, because there aren't that many boat crashes because there's a great deal of safety record, right? So I might have to generate that synthetically. I can do that visually. Whereas sometimes generating, something like cancer data or data for a rare disease might be a lot more challenging because we might not know all the characteristics, right, that make that synthetic data as accurate as possible. Then we have something like partially synthetic data. So partially synthetic data replaces parts of the data with generated data. This is more common. For example, it may replace sensitive characteristics like names, social security numbers, addresses, and the like. So you can get this kind of partially synthetic data where I go, look, we've got all this PPI, we've got to get it out of there and not use real social security numbers. So we're able to kind of strip that out, put in fake social security numbers and names, et cetera, without kind of damaging the data. That's incredibly useful for security and things of that nature. And then hybrid synthetic. And this is data that comes to us with both real and synthetic data, similar to how we might use semi-supervised learning. We might do the same thing here, where we're able to kind of look at the data, look at the various features and characteristics, and generate more versions of that in order to train the model to kind of expand the set, make sure that we're able to have enough data to really handle this. Current trends in the next 5 years, synthetic data is poised to be a major accelerator of AML. If we look at the scaling laws in artificial intelligence, most of the folks assume that if we just trained a bigger model with more parameters, that was going to be enough. But we found we need to really scale the data much more rapidly than the model itself. And so sometimes that data is available and sometimes it's not. And so being able to scale this synthetic data rapidly, and by the way, also be able to label it simultaneously as it's being generated, is a tremendous boost in terms of bottlenecks. So a lot of people are pouring energy into this. And we advise anyone, though, looking at synthetic data to clearly understand what problem they're trying to solve right now. And to understand very clearly and research the abilities and limitations of synthetic data for your use case. If you're doing computer vision, you might have a lot of choices, but if you're generating, if you're a financial institution looking to protect customer data, you certainly have some robust choices. But if you're looking to invent novel fraud use cases that the bad guys haven't thought of, you're not going to find much help there yet. You're still going to need to be able to collect that data over time as the infinitely creative and inventive thieves learn how to steal in a new way that you didn't think of, right? So make sure you have to make your decision. You've outlined your use case clearly. Make a short list of the teams that might meet those needs by looking carefully and critically at their offerings and the teams that support those platforms. That's a lot of ground to cover. We've covered a tremendous amount of space. The good news is there is a tremendous amount of innovation happening in AI and infrastructure space. It's not the early days where everyone's going to write their own stuff from scratch, reinvent the wheel, figure it out. Right now, with so many platforms in the ecosystem, it's challenging for any one team to get their heads around all that. And of course, not all parts of the ecosystem are equally developed, right? Some parts have seen rapid growth, like labeling accelerated by machine learning, are still developing and have more room to grow, like synthetic data. In some areas, like orchestration and pipelines, there's tremendous amounts of competition, while in other areas, like training, there are a few strong choices. Areas like AI supervision with monitoring, observability, and explainability are seeing quick improvements in adoption. And the good news is you got a lot of choices, and different parts of the ecosystem are incredibly far along, and you've got a lot of pieces to choose from. Other parts, unfortunately, are not quite as far along, and so you're going to have to figure out how important those are, to your pipeline, to your ML systems, and keep an eye on them over the course of the years. But the good news is really there's never been a better time to be building these systems. You've got a lot of pieces that you can pull in together to build capabilities that I think even the big gigantic tech companies could only dream of having 5 or 6 years ago, and you can get them out of the box. So that's a tremendously exciting time to be in this space. We expect it to change rapidly year over year. We're going to do one of these reports every single year to give you kind of an overview of how things have changed. It's changing quickly, but the good news is for you that you've got a lot of choices. And the nice thing is that if we sort of wrap it up right here, we say, look, how do you, kind of categorize your company? And this is sort of the last thing we want to say. More and more companies are moving into machine learning. And so, very few in terms of the people that we've sort of surveyed hadn't even started using it. But more and more companies, 41% of them are using it in multiple areas of their business. Some of them already have an AI/ML first culture, or even have a complete business model built around it. This is really going to only grow over time. And so we encourage every team to figure out how to use AI/ML in their systems, in their current business, whether they can extract new value from it, build new business models out of it. And you've got a tremendous amount of tooling to choose from in this space. The growth of any team is a journey. And at each stage, you're going to need different tools. At an early stage, you're going to need a few top-notch data scientists, and your tooling needs are much simpler. As your team grows, though, you're going to need newer and better tools to deal with that growth. AI is going to affect every single industry on Earth, from telecommunications to finance to healthcare to defense, construction, manufacturing, agriculture, and automotive. There is not a single industry anywhere on Earth that won't benefit from more intelligence. There's nobody out there saying, I wish that my sales pipeline was dumber, or that my supply chain was dumber. Everybody out there is looking to build in more intelligence, and it's only going to accelerate over time. But without the right infrastructure tools, organizations can't build those world-changing applications. AI/ML infrastructure is the foundation. The stacks of today and tomorrow are the foundation that allows the intelligence revolution to happen. Once those tools mature, the entire industry will move forward into early majority stage, and we'll begin to see more and more applications that we simply can't live without, and that we couldn't possibly create with traditional programming. And that's the beauty of it. The AI/ML infrastructure is the foundation on which to build those applications of tomorrow. So choose wisely. Thank you very much for your time. Again, I'm Daniel Jeffries, Managing Director of the AI Infrastructure Alliance. You can find me on Twitter, LinkedIn. You can go to ai-infrastructure.org. download the various blueprints, download the report for free, get it in your hands. I will put a link at the bottom, and come in, join our communities. If you're an AI infrastructure company, we'd love to have you. Just come in here and support our efforts, and so we can continue to put out the best and most important and neutral information in the space to help everyone make better choices. Thank you again for your time. Most appreciated. Have a wonderful day and enjoy the rest of the conference.